It's 4 o'clock. Let's go ahead and get started. So today we're going to cover most of the geometrical theory of diffraction, the GTD. We're going to learn about the shortcomings of GTD, how it predicts infinite field at the shadow boundaries. And next time we're going to learn out ways to fix this problem using the theories of uniform asymptotic theory and uniform theory of diffraction. In order to understand those, or maybe not in order to understand those, but part of your homework has been shifted to read a paper that's on UAT, right? I don't know if you guys all got the email, but that's a very good paper, and it goes through GO and GTD and all that, so it builds everything up, and it's written by the same author. We're taking a lot of these material for these notes of this course, so I think it's a good paper for you guys to read. All right. All right. Don't wait to start on your homework for your ray tracing program. That's an important problem, and there may be some difficulties with it. Right? It's not as simple as you might think. So get started on that. Okay, good. We have three lectures left today, and then the 2 next week, and we're done. We're going to do GTD today, UAT and UTD next Monday, and then next Wednesday we're going to do a little bit about Green's functions, the last chapter in your book, and that'll be it. All right. Okay, so let's get into it. Geometrical theory of diffraction. So consider a typical diffraction problem with a conducting screen sigma with an edge gamma now, a zero angle wedge. So this is a very sharp screen here, and it has the edge gamma, and the screen is still called sigma. All right. It's being illuminated by an incident field, E incident. The asymptotic solution of the total field is to be determined. So we already learned how to calculate the geometrical optics field, which we're now calling EG. That contains 2 fields, E incident and E reflected. The screen itself blocks E incident, so there's a shadow region with the indicator epsilon incident. And then there's a reflection shadow boundary for the shadow indicator for the reflected field. The geometrical optics field fails to predict a field in the shadow zone. And we know that there's field in the shadow zone. So therefore, it fails to account for the diffraction phenomena. All right, to account for diffraction, we'll introduce Keller's theory of diffraction. All right, in this theory, an additional component of E total is introduced. We have EGO. E total now is comprised of the geometrical optics field and now E diffracted. All right, so we have totally we have E incident plus E reflected plus E diffracted. All right. E diffracted now is going to contain 2 components as well. That due to the incident field and that due to the reflected field. And its asymptotic expansion is now dependent on k to the 1/2 order. K to the minus 1/2, sorry. K to the minus 1/2. So it's half integer order, all right? It still has its own iconal and its own ray, phase function, and all of that. And it's also an asymptotic expansion in terms of inverse powers of k, but instead of inverse integer powers of k, now it's inverse half integer powers of k. All right, and so you have the same phase function for the incident and the reflected based diffracted field, but they have different amplitudes. All right, okay. So here's the diffracted field. We can make some preliminary remarks about it. The diffracted field is of order k to the minus 1/2, and it is asymptotically smaller than the geometrical optics field, which is of order k to the 0. In general, E diffracted is non-zero everywhere. There are no shadow region indicators for the diffracted field. And just as the geometrical optics field contains 2 symmetrical parts, the incident and the reflected field, the diffracted field also consists of 2 symmetrical parts. We call E diffracted incident associated with the incident field, E diffracted reflected associated with the reflected field. These 2 parts have the same phase function but different amplitudes. Since the diffracted field is an asymptotic solution to Maxwell's equations, it of course should satisfy Maxwell's equations. All right, we looked at the law of edge diffraction last time. So the surface is S diffracted equal to a constant. S diffracted equal to a constant. Define a diffracted wavefront which is orthogonal to the diffracted rays. All right, all diffracted rays emanate from the edge gamma on the screen. So this edge gamma here, this edge gamma, all of the diffracted rays emanate from that edge. What does that mean the edge is? What would you call that edge if all the rays emanate from it? Source is a good word, but caustic, right? So the edge is an automatic caustic of the diffracted field. All right? All right. Consider an incident ray in the direction sigma incident. So here's sigma incident, this vector here. That ray meets edge gamma at some point O. This is the point O. It's the point of diffraction, and makes an angle beta incident. So we can say that this is beta incident with the tangent T of gamma. So here's the tangent, the ray tangent, the edge tangent. Such a ray gives rise to a family of diffracted rays which emanate from O and make the same angle beta with T, or make some angle beta with T, right? We're going to see that beta is equal to the beta incident. Okay, so in other words, each edge point R illuminated by E incident generates a cone of diffracted rays with cone semi-angle beta and vertex at the edge point and axis the tangent to the edge. All right? The fact that beta equal to beta incident is known as the law of edge diffraction, which is the counterpart to Snell's law. So we have some incident angle here, beta incident, right? With this edge tangent. All rays that make, from this point, springs forth a whole family of rays, a whole cone of them. All rays which have that same angle beta, so let me draw the one that they drew in the figure here. All rays which make this angle beta with the ray tangent, the same as the incident, are admissible. So you get all the rays, the whole cone of them, all right, a whole family of them. You guys remember in ECE 5105 last semester when I did the demonstration, we solved the oblique scattering from a cylindrical wire, infinite wire, right? And we had that metal rod, the pointer, right? I extended the pointer and I took a laser pointer and shined on it. And we looked obliquely. What happened? We saw that there was a circle, a cone generated. Very similar to this, right? So you can get an entire cone of exactly the same thing. All right. So the diffracted wavefront. Now we got to calculate what the amplitudes are. What do we need? We need the radii of curvature of the diffracted wavefront, right? The diffracted field is a wavefront. There are rays. We know where the rays are now. They start with they emanate from the edge, and they have a whole cone of them with the angle beta equal to beta incident. But now we need to find the radii of curvature of this diffracted wavefront. So we can calculate the amplitude. How do we do that? We're going to use phase matching again, all right? So consider a particular diffracted ray in the direction sigma. So here's a diffracted ray in the direction sigma, and passing through the observation point R. Here's the observation point R. Now we're in the ray coordinate system. In the ray coordinate system, remember we have three vectors. We have alpha, we have beta, and sigma here. And there are there's a length and two angles. R is, or sigma rather, is like R. And theta, so it's with respect to this origin typically. So you could move this beta here and this alpha here, right? Beta it takes the place of theta, and alpha takes the place of phi. So it's a spherical coordinate system. All right? Different betas and thetas. So beta's fixed here, right? Beta is going to be the beta incident, this angle. But alpha varies. So phi generates your cone, right? All right. So out of spherical coordinates, the spherical coordinates of R are sigma, beta, and alpha, where sigma is the radial distance, beta is the polar angle, and alpha is the azimuthal in the plane perpendicular to T. So this is like your z-axis now, right? And the plane perpendicular to T, which is in this direction, is the polar angle is measured from T okay, so this is like theta, right? So this is beta. And then let's say here's X and this is Y maybe. Then the azimuthal angle is measured just like it is which is equal to alpha, right? All right. Okay. The phase of the diffracted field at R is given by, so this phase function of the diffracted field at this point R, this is the point R, measured from this origin, so it is this ray, right? The position vector, is S incident at the point O, whatever the incident field phase was at that point, plus sigma. And sigma is nothing but the length along this ray, right? This coordinate here is the length of the ray from the point O. All right, where SI is the value of S incident at O. Proceeding along the diffracted ray through O and R, so you go through O and you go through R, the principal directions of the diffracted wavefront remain the same, right? Since the edge itself is a caustic line of the diffracted wavefront, one of the principal directions will be in the plane containing sigma and T, right? So remember, what are the principal directions, right? The principal directions are the directions where you have minimum and maximum curvature, right? If we have an edge as a caustic, then that's going to give us it's going to give us maximum curvature in that direction, right? Or sorry, minimum rather, maximum radii. So that's one of the principal directions. So one of the principal directions will be in the plane containing sigma and T. So here's sigma, right? And here's T. All right. And the other will be orthogonal to this. So sigma crossed with T gives you a vector orthogonal to sigma and T, which is the vector orthogonal to the principal direction, which is in the plane of sigma and T. So look here. Here is sigma, here is T. So sigma and T make an angle beta between them, right? Because we know beta incident is equal to, here's sigma here. So this one is sigma, right? So this angle here is also beta because this ray, sigma, is in the cone, in the diffracted cone, right? So that angle beta is here. So beta is an angle between sigma and T. And if you take the cross product of these two vectors, you get one orthogonal to those two, all right? So that's sigma 2. Now, the definition of that is sigma hat magnitude, T hat magnitude, sine of beta, sigma 2 d directed, right? So if you divide through by this, because these are both unit vectors, they have magnitude 1, then you get the following definition for sigma 2, all right? So that's one of the principal directions of the diffracted wavefront. The other one you get by crossing that with sigma again, right? Which gives you one in the plane of, gives you this one, all right? So then you end up with the right-handed coordinate system, sigma, sigma 2, and sigma 1, all right? Good. So now we need to express our incident pencil in the coordinates of the edge, right? So that we can do phase matching, just like we did for the surfaces. So in the Fresnel approximation, so we have a sharp edge here, right? The sharp edge is gamma, but it's a curve in space. It's not a surface because it's a sharp edge, right? So we're going to use a parameterization of a curve, and we're going to use the Fresnel approximation of a space curve. I don't know if you guys remember that from our study of differential geometry, but what it says is R of sigma. So there's some reference point here. Well, okay, so we'll get to the reference point, but R of sigma, so about some reference point in an amount sigma is approximated as R at sigma naught plus sigma minus sigma naught into T hat, which is the linear approximation, and then sigma minus sigma naught squared over 2 times the curvature in the normal direction, which gives you a planar curve still, right? Because the torsion hasn't been introduced yet. And it now has curvature. It's a 2-dimensional approximation or a quadratic approximation. And then you add the cubic term, which has torsion, which lifts your curve out of the plane spanned by T and N in the direction of B, the binomial, right? All right. If we take our edge and apply this approximation to it, our distance parameter is now eta instead of, okay, so here's the reference point on the edge. We measure eta to the point O here as this distance, all right? So we need a distance parameter. So we take some reference point here, right? No, sorry. That is correct. This is the reference point O. But this point is some point on the edge, which is eta away from the reference point. So it's measured that way. When eta equals to 0, you're at O, all right?
So the edge is represented by a curve?
Yeah, this is a sharp edge, right? It's a very sharp, like a thin screen, piece of paper, but made of metal, right?
Is O also where like sigma naught is?
Yes, so sigma naught is, yeah, so this is the general formula that we had from differential geometry. We're going to specialize it to our curve now, but sigma naught is the central point of your Taylor series expansion of the curve, right? Okay, so about point O, we're expanding this curve in this Fresnel approximation. So as we move down the curve, we're moving a distance eta, all right? So eta takes the place of sigma, basically. So making use of localization. Localization is a key concept in geometrical optics and geometrical theory of diffraction and ray optics. What it means is that the ray, so all of the phenomena, reflection, refraction, or diffraction, all of that only depends on the environment of the scatterer and the wavefronts locally to the ray. So you might have a big surface, but only the local geometry around the intersection point of the ray matter and contribute, right? So what you can do then is you can use what are called canonical problems that mimic the geometry locally. We'll do that for diffraction. You'll see what I mean. But it's a big concept, localization. The curve just above and below the point O will always be in the osculating plane. In other words, we have zero torsion. Why is that? Because here we're saying that the curve locally around O, we're going to say is a planar curve. We're going to use no torsion, right? It's a straight edge, and it's going to be in that plane, all right? So locally, the edge can be described then locally using the first two terms, right? So at the point O, the leading constant term is zero, right? And then we have the sigma naught is zero, basically, or we're expanding about the point zero. So then we just have sigma, which is now eta, multiplied by t. And then we have, so now sigma is zero, but this is now eta. So you get eta squared over 2. And then you have kappa and n hat, all right? Okay, good. Now we're to perform phase matching. So we need to set the incident pencil's phase function equal to the diffracted pencil's phase function, and to get the diffracted wavefront curvatures, all right? So we need to express the incident wavefront in terms of the curve coordinates. How do we do that? Well, we want to find first the component of sigma 1, the component along the sigma 1 incident axis, right? All right, but in terms of the coordinates of the curve. So the way we do that is we take the dot product of r of eta and sigma 1 incident, all right? So this is, where is the incident wavefront? Okay, anyhow. So take the dot product of sigma 1 with their expansion for the curve. So we have this, right? And if we do the dot product, we distribute this dot product, we get eta into t, right? Because t hat dotted with sigma 1 incident. Oh, that's what we have, eta sigma 1 incident, right? And everything else is dependent on order of eta squared. So we're going to ignore all that, all right? We're talking about locally. So sigma 1 becomes eta t dotted with sigma 1 hat. If we go back to this kind of coordinate construction here, then we can say that that's equal to, okay, so eta is there. Now let's take care of this dot product, magnitude t, magnitude sigma, cosine theta, plus the order of the eta squared. Well, that's equal to eta cosine theta because these two are unit vectors. And then we can say cosine is 90 minus beta, and we can write that in terms of beta, where theta and beta are defined here, right? Okay, good. So that's the sigma 1 coordinate. We repeat now, so we can write this, so this sigma 1 coordinate is there. So these are the coordinates of, this is the angle of the, okay, so eta is a parameter along the edge, right? The distance parameter, and beta is the incident angle. All right, now this result is valid for when t sigma 1 incident and sigma incident are all in the same plane. So t sigma 1 incident and sigma incident are all in the same plane. That may not be the case, right? As a matter of fact, it probably won't be. So let's look at this wavefront. We have the ray tangent is here. So this is the tangent to the edge. So let's say the edge is in that direction. We have sigma 1 here is like that. And we have sigma 1 incident would be in this, would be this axis, right? Okay, but the tangent to the ray, these are all planar, right? But the tangent to the ray may not be in that plane, right? How many vectors span a plane? 2, right? So the sigma incident and the sigma 1 incident, those two vectors already span a plane, right? Let me draw it like this. So here's green. This plane is spanned by sigma incident and sigma 1 incident. But let's say that the principal direction of the incident wavefront doesn't align with the plane spanned by, say, sigma and the ray tangent. Then you just need to rotate it, right? So you add this cosine of, so look here, this is the easy way to understand this. So, okay, so let me first finish my sentence. So to rotate sigma 1 incident to line up with the principal directions of the incident wavefront, all right? Okay. So then we get eta sine beta cosine omega, all right? Now, what is this? So look at here. Here's a XYZ coordinate system, and here's some ray tangent, right? The angle beta is the angle between the sigma incident, right? And the ray tangent, right? So this vector here, this tangent basically, you can say has this kind of spherical expansion in that coordinate system, because it looks kind of like r sine theta cosine phi, and here's the other one, r sine theta sine phi, right? Kind of looks like, and that's exactly what this angle omega is. It's the one in the xy plane that rotates you to. So it rotates, this is now going to be the sigma, right? You want to rotate sigma 1 incident to line up with the principal directions of the incident wavefront. It's a coordinate system that we're erecting to affix to the wavefront itself. All right? Okay, so you find sigma 2, sigma 1. Okay, so for the sigma incident component, we do the same thing we did before, r dotted with sigma incident. All right, if we work that out, here's our r, here's sigma incident. We get eta t dotted with sigma incident. We get 1/2 kappa eta squared n dotted with sigma incident. And we know what the first term is. It's eta beta, or eta cosine beta incident. And the second term remains the same. All right. Now that we have these three components, we can write the phase function of the incident wavefront in terms of the edge coordinates. So now we're going to write the incident pencil. Here's the incident pencil, sigma 1 incident, sigma 2 incident, sigma incident, in terms of the coordinates of the edge, right? So the coordinates of the edge are eta and beta. All right, so n omega. So let's do that. So sigma incident is the phase function of the incident pencil along the direction to the point of diffraction, right? Along the axis, along the ray, axial ray. Then we have, since we're in the principal coordinate system, this is our quadratic approximation of a surface, 1/2 of, x dotted with q dotted with x, right? Okay, good. This is just the incident pencil so far. We haven't even done any expressions in terms of the edge coordinates. All right. Now, so sigma incident we know is eta cosine beta I, right? So here's sigma incident dotted with the edge coordinates is that. All right, and this is sigma incident rather. So, okay, so this is sigma incident, right? So sigma incident gets replaced by that plus this, right? So here's that as well. This is all sigma incident, yeah? All right, then we have this second order approximation to deal with. Sigma 1 incident we calculated here, so we replace that. Sigma 2 we calculated here, we replace that, okay? All right, now we factor out a 1/2 and eta squared because it's eta here and we're going to square it. So we factor all that out and we get eta squared over 2 and then the remaining terms are here, right? Okay, I don't know if you remember what this looks exactly like. What? Do you guys remember what that looks like? This part. It's from, was it last homework or this homework? It must be this homework, right? I don't know if you've done your homework yet. No, it was last homework. What is it? Euler equation. Very good. If 1 over r is kappa, then it's kappa 1 times cosine squared of some angle, right? And that angle is in the tangent plane. So Euler equation. Very good. All right, so we can write that then as, we're going to write all of this as 1 over r1. All right, good. So you'll see why. Okay, so now, so having noted that this is 1 over r1, so that's the curvature in some direction by Euler equation, is an interpolation between the two principal curvatures, right? So this curvature in some direction, the direction that omega I is pointing. Remember, what is Euler equation? Kappa t hat, kappa 1 sine squared, what angle do we call that? Alpha, plus kappa 2 cosine squared of alpha, right? So this is the same thing. So we're saying, and if you write this in terms of radii curvature, it's 1 over, so the analogous here is 1 over ri incident of omega is equal to 1 over r1 incident sine squared alpha plus 1 over r2 incident cosine squared alpha, right? Which is this. Okay, good. Fine. Okay, so that now is this, right? So the diffracted wavefront can now be written by simply replacing superscript I by superscript D. Okay? All right. Now that we have both of them, since we have set up the diffracted coordinates to be in the principal directions, then we know this angle is 0 because that angle measures the angle with respect to the principal directions, right? Okay. But the diffracted wavefront's going to be in the principal directions. So we're going to assume that omega d is equal to 0. That means that t hat, sigma 1 diffracted, and sigma diffracted are all in the same plane, because we defined that angle omega as the angle that you needed to rotate away from that plane containing those three vectors to get for t hat and sigma hat to be with respect to sigma 1d. All right. Then, with these assumptions, then 1 over r naught d is just equal to, so then we have, remember, this is 1 over r naught diffracted, omega diffracted, is equal to 1 over r1d times cosine first, I think, omega plus 1 over r2d sine squared of omega diffracted. Okay, so if omega diffracted is 0, then we get a 1 here and a 0 here. And that means we just get 1 over r1d. What does that say? Well, I wrote it here. It shows that the edge is acoustic, right? For the diffracted wavefront. One of the curvatures is 0 at O. Sorry, yeah, one of the curvatures is 0 at O, right? It's a caustic line. Locally, it's a line. Okay, good. We are now in a position to perform. Wait a minute. This can't be. I think that has to be infinity. I have a feeling that this is supposed to be infinity. Right? Caustic line means that R2, no. R2. Okay, let me think about that. Okay, we're now in a position to perform phase matching to find R1D. So, yeah, we first match the linear terms, all right? So we said this, which is S diffracted, equal to this, which is S incident, right? So they have similar terms. So if we match the linear terms, what do we get? Eta cosine beta diffracted is equal to eta cosine beta incident. And what does that mean? Beta incident equal to beta diffracted. We get the law of diffraction, a law of edge diffraction out of this phase matching procedure, matching the linear terms. When we did the calculation of the reflected Q matrix, and we matched the incident pencil to the reflected pencil on the surface, sigma, we found by matching the linear terms, process of phase matching, we got the law of Snell's law of reflection, right? So linear terms gave us Snell's law of reflection before, and now considering edges, because before we expanded the surface locally in a quadratic approximation, and we did the dot product of all the incident field vectors with those surface coordinates and of the reflected pencil with their surface coordinates, and we did matching of S incident equal to S reflected over that surface, quadratic second order approximation of the surface. Here, we're doing incident pencil S incident and expressing that in terms of a curve instead of a surface, and the diffracted pencil in the same, express it in terms of the curve coordinates and matching linear terms, and we get the law of edge diffraction now, right? Okay, matching the quadratic terms is this part here and here. If we carry out, let's see, by law of edge diffraction, beta incident and beta diffracted are equal, so we're going to call that one beta, this one becomes beta incident, right? And then from there, we can start to match things up. Kappa n dotted with sigma incident minus kappa n dotted with sigma diffracted plus this term here is equal to this term, all right? And we can then solve for this by multiplying, we're dividing through by sine of beta incident. So here's the divided through by sine beta incident. It cancels this one. And we end up with this expression. This is an important expression right here, all right? So the radius of curvature in some direction, omega naught, with respect to sigma 1 in the tangent plane of the diffracted wavefront. Why are these incident? That's in terms of the radius of curvature of the incident. The curvature of the edge comes into play, right? It affects the radius of curvature. If I have a very curved edge and I come in with a plane wave, for example, then we know one of the radii of curvature is going to be 0, basically. The other radii of curvature is going to be dependent on that curved edge, right? The curvature of that edge. And then we have sigma incident minus sigma diffracted dotted with n, okay? So this is the curvature in the n direction, right? All right, good. So now we've calculated what the diffracted wavefronts radii of curvature are, right? Very good. That's a great question. So a corner is the third kind of diffraction. We're not going to study that in this course. But so there's half plane diffraction. We're going to study wedge diffraction, which is like a corner. But then there's vertex diffraction, where things come to a sharp point, right? That is k to the minus 1 order diffraction. Geometrical optics, the rays, is k to the 0. And then diffraction from edges is k to the minus 1/2. That's what we're studying now. And diffraction from vertices is k to the minus 1. All right. So here is the, okay, so since we determined that R0 diffracted is equal to R1 diffracted, then we get the following. If you invert everything in, or write this in terms of curvatures. The curvature of the diffracted wavefront in the one direction is equal to the curvature of the incident wavefront plus kappa over sine squared of beta, where kappa 0 incident is the curvature of the incident pencil in the t hat sigma incident plane. That's the one that sees the curved edge, right? That's the one that sees the edge. And kappa is the edge curvature. Kappa 1d is the curvature of the diffracted pencil. All right? You remember where this comes from, right? We determined that here. Because we're in the principal directions, omega d is equal to 0. Then that means that 1 over r naught d is equal to 1 over r1 d. All right, so we use that fact here. All right, good. So, good. So we have now the curvature of the diffracted wavefront. Let's calculate the diffracted field amplitudes. A typical point on the diffracted ray is described by the spherical coordinates sigma beta alpha. For a given incident field, beta now is a function of eta. For a given incident field, beta is a function of eta, where eta is the arc length along the edge, gamma measured positively in the direction of t. This edge is very curved, right? So it's like that. Then at this point, the beta is going to be different then at this point where the tangent is changing, right? So this same incident ray is going to make a different angle. All right? All right. So then eta, alpha, sigma form diffracted ray coordinates. Now we have a new coordinate system of diffracted ray coordinates. Performing the phase matching as we did over the edge gamma led to this expression, which we just derived by phase matching. All right? So here are not incidents. The radius of curvature of the incident wavefront at O in the plane through T and sigma incident. We had mentioned that. And this radius in terms of the principal radii of curvature and the principal directions of the incident wavefront at O is given by this Euler equation, right? All right. Good. Omega I is the angle between xi and the projection. Okay, so this is just defining these angles. And the edge itself is a caustic line. So this is kind of a width radius, and hence the other radius of curvature, R2 is equal to 0. So it is equal to 0. R2 is equal to 0. All right. Good. The continuation of the diffracted field amplitude for the leading term of the Lüneburg-Klein expansion of the diffracted field, the leading term with respect to O is incident and reflected diffraction. And we have the following. We have sigma to the minus 1/2. So we're doing this in terms of sigma. Sigma to the 1/2. The square root of 1 plus, so you have to invert this after, right? So this becomes minus 1/2. So you get 1 over square root of sigma. And square root of, and then the divergence factor with the other wavefront, right? Or the other radius of curvature. So it's like the divergence factor. But one of the radii is 0. All right. And the initial values of the incident field amplitude or incident field at the point O of diffraction plus sigma to the 1/2 plus the reflected ray, right? Okay. We can determine the initial values by using canonical problem of Sommerfeld half-plane diffraction. All right, that's what we're going to do. We're going to study Sommerfeld's half-plane solution to the Sommerfeld's half-plane solution. And that locally, this canonical problem locally looks like, so if I have a curved edge, then some ray coming in here that's incident locally around here, this looks like a sharp edge, right? We can approximate it as an infinite edge, an infinite sharp edge. Solve the problem which we can solve analytically of a plane wave reflecting or scattering off of a very sharp edge, infinite sharp edge, and use that solution locally here to determine what the diffraction coefficients are. So just like there's a reflection coefficients and transmission coefficients, there's a diffraction coefficient. If I have a plane wave that's illuminating some kind of PEC, there's a reflection coefficient. If I have a plane wave illuminating a dielectric interface, there's a transmission coefficient. Now if we have a plane wave illuminating, or a ray, which is locally a plane wave, illuminating a sharp edge, we have a diffraction coefficient. But to calculate these diffraction coefficients, we're going to have to solve the Sommerfeld half-plane solution and compare that exact solution to our diffracted ray form and see what part of that expression is the diffraction coefficients. All right, so let's do that. This is justified since high-frequency diffraction is a local phenomena, and locally, the screen can be approximated by a half-plane. Half-plane means that this goes off to infinity, and then there's nothing here, right? If it was a full plane that infinitely cut the universe in half, that would be everywhere, right? But a half plane, it's half of that plane, right? All right. The screen, okay, so once these initial values are found, the diffracted field expansion at some point R can be determined. So if you do that, the final result is here. The diffracted field is given by this G factor, G of K sigma, multiplied by 1 over 1 plus square root of 1 plus sigma over R1. That's our divergence factor. Then we have this chi I, which is going to be our diffraction coefficient. So we have to be careful. There's diffraction coefficients of scalars, and then there's ones that we're going to package into a diffraction coefficient tensor. All right, so they're a little bit different. There's a coefficient that's different about them. Sine beta is there. And we have e to the IKS incident, and then this rotation operator that rotates the incident electric field within that cone so that you can find the diffracted electric field components. And then we have the same thing for the reflected, all right? Okay, so let's study these pieces. Cylindrical wave factor here, this comes from the leading term of the asymptotic expansion of the two-dimensional Green's function. Why do I have, let's see if you guys pick up on this. This is what kind of wave is this? Incoming or outgoing? What? Why? You're right, but why? Last semester we had H01, H02.
Yeah.
Which one was outgoing?
So we want to let 0 to be non-zero and infinity to be.
So remember, last semester we had H02, let's say beta rho, which was J naught beta rho, and I think it was minus J Y naught beta rho. Then we had H naught 1, which is equal to J naught plus J Y naught beta rho, right? What are the differences between H1 and H2? Conjugate, right? Which one radiated outward last semester? 2. 2 was the outward wave, outward cylindrical wave. 1 was a converging cylindrical wave, right? It was converging to the axis. Okay, but what time convention are we working with this semester? Or not this semester, but this topic? Ray optics. That's right. We're doing e to the minus I omega t. So H1 now is the outward wave. All right, so you got to be cognizant of that. Now, do you remember last semester, our Hankel function, we did the large argument and small argument expansions, right? You probably didn't know, but those expansions are asymptotic expansions, right? So the leading term of the asymptotic expansion of the cylindrical wave that we had, the outgoing wave, was this, all right? So that's the leading term. All right, so that's the cylindrical wave factor. It's coming from the edge. Then we have the divergence factor. So the product here, so the product of G multiplied by this divergence factor behave as a cylindrical wave when sigma is equal to 0. When is sigma equal to 0? What is sigma?
Distance,
What is sigma?
length of the arc.
No, that's eta. Sigma's the length along the diffracted ray, right? Right, it's in the axial ray. It's the length, it's the arc length parameter along the axial ray of the diffracted field. All right, so what are these two together? Why are they written like this? When sigma is equal to 0, what happens? When sigma is equal to 0, we get sigma to the minus 1/2 behavior when you multiply these two together, which means right near the edge, it's a cylindrical wave, right? That long edge, that sharp edge is what's dominating the diffracted wavefront shape, right? And as sigma goes to infinity, what happens? We're far away from an edge. Locally near an edge, that's all there is, right? That's the whole world next to the edge. But when you go infinite far away, that edge becomes a point, and you lose all the information of that edge, and you become a spherical wave. So these two multiplied together give you sigma to the minus 1, which is a spherical wave as you leave the edge far away from it, yeah? Okay. All right, so then we have the phase of the diffracted field here is S incident is the phase of the incident field. The phase of the diffracted field is given by the phase of the incident field plus the sigma to the observation point along the diffracted ray, right? All right. Then now let's look at this rotation operator. So the rotation operator, all the rotation operator does is take, it rotates the vector component. So see this vector components here, right? This is alpha, this is beta, and then this one is sigma hat, right? Now, the incident field here, let's say the incident field, here's sigma incident, right? Sigma incident, and there's also some, let's see, the sigma coordinates are going to have, we can call it x1 incident and x2 incident, but if you propagate those up here, then you have these two vectors, right? What all we're doing with this rotation operator is rotating the incident field vectors along this cone to this point. So it's just a rotation operator that takes this right-handed trihedral and rotates it along that cone. All right? Okay. So in the end, it depends on the incident angle. And, all right, so let's read through it real quick. Okay, the rotation operator denotes the rotation about the tangent. So here's the tangent, rotation about the tangent that brings sigma 1 incident, or sigma incident rather, sigma incident onto sigma hat. All right? So rotation of sigma incident, if I rotate this vector around this cone, then I rotate through that angle and it brings it to be aligned with sigma hat, right? So if I rotate the incident field vector, it brings it in line with the diffracted rays. The incident K vector, I apply the rotation operator to the incident K vector, if you will. And I rotate that to align up with the diffracted rays axial ray vector, right? That's what that does. So we introduced the unit vectors, beta incident, and beta alpha, which are the diffracted rays. The beta alpha is the diffracted ray, right? They're here. Pointing in the direction of increasing beta alpha and therefore orthogonal to the ray. The amplitude E naught incident, the incident ray, may be resolved into two transverse components. So the incident electric field amplitude is going to have a beta component and an alpha component of the incident field, all right? And E naught incident beta and E naught incident alpha are the polar and azimuthal components of E naught incident. In other words, this is theta hat and phi hat for a ray fixed coordinate system. So rotating operator operated on that E naught incident brings it in line with beta and alpha. Here's beta and alpha. But it has the same components, right? At O now instead of at R. Okay? So if we expand all this, we get 1 over sine squared beta. E naught incident dotted with the tangent. That's now a component. That's a scalar, right? E naught incident dotted with the tangent is a scalar value. And we affix that to this vector here, which is sigma cross T crosses sigma. What is that? Sigma cross T cross sigma. Do you remember? Sigma cross T crosses sigma. Let's go back to our coordinate system here. Sigma crossed with T is here and crossed with sigma. So sigma crossed with T gives us this vector, right? Okay, look. Here's 1 over sine beta sigma cross with T. Then we take that and we cross it with sigma again to get sigma 1 hat. So sigma 1 hat is equal to sigma 1 hat is equal to 1 over sine of beta sigma hat cross with T hat cross with sigma hat, right? So that's nothing but this axis, the sigma 1 axis of the diffracted, right? So let's go here. Where are we? We're at the rotation operator. So here's our sigma cross with T cross with sigma. And here's the 1 over sine beta. One of them, right? And then that's E naught dotted with T. So we take the tangent component and we assign that to this vector sigma 1 diffracted hat. Sigma 2 diffracted hat is this vector here, T cross with sigma. And we just take the incident field and we dot it with that. All right? Okay. So now, okay, good. So now we have the reflective field component and incident field component. They have their own diffraction coefficients. So at the point of diffraction, at the point of diffraction, the reflected field is simply related to the incident field. All right? So in particular, we have S reflected equal to S incident, yeah? The phase is the same of the reflected field as the incident field at the point of reflection, at the point of diffraction, right? At O, they should be the same by phase matching. So, and then we have the reflected beta component is negated because it's tangential, but the alpha component is not. So if we use these, because the total field, okay, remember when we did plane wave in last semester, we did a plane wave obliquely incident on a dielectric interface. Dielectric half space to the left, free space to the right, and I came in obliquely, right? what were the three fields that were present at the interface that we had to do phase matching of? The total field is incident plus reflected plus transmitted. All three are there at the interface, right? So that's what's going on here. All three of these fields are at the point of diffraction. The incident field the incident field and the reflected field are there at the point of diffraction. And there's also the diffracted field. But anyway, the incident field and the reflected field are related, and we know how, so we can combine those two, and now we have our diffracted field here, which is equal to G of K sigma plus this, plus the 1 over sine beta, e to the IKS incident, the incident field phase at the point of diffraction. And now we have beta hat, alpha hat, the components of the incident field there, and these coefficients. These are called the diffraction coefficients, ds and dh. ds is d soft, and dh is d hard, and they're related to these diffraction coefficients, chi I and chi r, through this relationship. So the soft diffraction coefficient takes the minus sign, the hard diffraction coefficient takes the plus sign, and these are the incident and reflected diffraction coefficients. So we'll study those now. So we can rewrite this now as this, and this you'll see this form a lot, where we have e to the ik sigma d. So what do? We go to the diffracted field Lunenburg-Klein expansion and keep only the leading order term. That's the only term that Keller's theory predicts. So we keep m equal to 0, means we pick up a k to the minus 1/2 and e to the ik as d. So here's e to the ik sigma d now, and the k to the 1/2 is there, right? Otherwise, everything else is the same. So then we have this, and these, so then this G factor, what was that G factor? Remember, the G factor had this all in it, right? So if we go back here, this is all over here. These diffraction coefficients are appearing here in a matrix now, and we've kept these terms outside. And we call this D, which is the diffraction tensor, diffraction coefficient tensor, dotted with the incident field, where the incident field is evaluated at the diffraction point. All right. Okay. All right. So note D and DS nature, the sound soft, sound hard scalar diffraction coefficient obtained from canonical problem solutions. We're going to derive these now. We're going to study those next. And to do that, we have to solve Sommerfeld's half-plane problem, all right? Okay, so the key idea is to use localization to find canonical solutions which mimic the geometry locally so that we can find the diffraction coefficients. The problem we're going to study now is the scattering of an incident of a plane wave here, incident at angle alpha with respect to the x-axis of an infinite half plane of PEC. So it's infinite in and out of the board. It starts from the origin and goes off to x infinitely far away. All right? The observation point is rho and theta. All right, so consider an incident plane wave called U incident. So it's a scalar component of that vector, right? We're going to consider a single component here, all right? So this is that component. E incident, E ikxx plus ikyy, which is equal to, in this coordinate system, cylindrical coordinate system, e to the ik rho cosine of phi minus alpha. All right? Good. For soft polarization, we assume that this single component is this EZ. Z is in and out of the board, which is what kind of polarization here? TE, right? And that means that the tangential component is EZ, which is E, which is an electric field component, so it has to be 0 on the PEC by the boundary of tangential E goes to 0. Otherwise, for hard polarization, we're going to say that the component in and out of the board is the only component, and it's under consideration, is the magnetic field. And therefore, the magnetic field boundary condition is this, right? Okay, good. The Sommerfeld exact solution for the plane wave scattering from a half plane, go to this paper if you want to learn about this or to see the derivation, is the following.
This is in Jer.
It is. So, U total, 1 and 2 for soft polarization and hard polarization. The total field is equal to e to the ik rho cosine phi minus alpha. Some of you guys are going to say, we already solved this problem last semester, right? We're going to look at that. Do you remember when we solved this? Yeah, remember how do we get to this? We solved scattering from a wedge. And if you take the wedge angle to 0, we solved the problem of scattering from the exact series solution. We're going to look at that today as well. This function here is called the Fresnel function. It's an integral. It's given by this function here, and its plot is here in this plane. So I'll tell you about that plot, 1 second. Plus or minus or plus for 1 or 2, and then we get the basically the other component, which is the reflected field, basically, right? And then here's S1 and S2's definitions. All right, so this f function, which has all of this as its argument, is called the Fresnel function. It's an integral. They have them in MATLAB, and the Fresnel function, a plot of the Fresnel function using x as its parameter, right? So x is the parameter, so each value of x that I choose, I get a new result, right, from that integration. So I can plot it as a function of x. So at x equal to 0, what do I get? And this is a complex valued thing, right? So you get a complex result for a real input. So the real input is x. At x equals 0, I'm here. At x equals to minus 1, I'm here. At x equals to 1, I'm here. X equals to 3, I'm here. X equals to 4, x equals to 2, x equals to minus 2, minus 4, minus 3. All right? So it's called the Boersma spiral, and it spirals in, right? So that's what that function looks like. We use this function a lot in UAT, UTD, and we're going to use it here in our GTD formulation. So when we take Sommerfeld's result that I just showed you and asymptotically expand it for large values of k sigma, meaning so when we solve asymptotic integrals, that means we expand asymptotically this integral here. You guys did that in your homework. And you make a series out of it, and then you integrate each of those terms. We asymptotically expand for large values of k sigma. The diffraction coefficients can be identified. So what are we trying to do? We're trying to use this exact solution for the scattering off of this half space. We know the functional form of it, the exact series solution. Now we want to take an asymptotic expansion of it so we can compare the asymptotic expansion of that exact solution to our diffracted electric field and match everything up until the only thing that's left is the diffraction coefficients, right? Remember, we have this. This is our diffracted field, and we don't know what d soft and d hard are yet. But we're going to use an exact solution of the diffraction of or reflection scattering from a half plane, rather. And we're going to say, oh, I see this term, this term, this term, this term in the exact solution. So whatever's left, we can find out what diffraction. By using the localization and saying locally that edge looks like a half plane infinitely, an infinite half plane. It's not mode matching. We're just matching up the expressions. We will do mode matching later. Okay, so all right, so take that solution, asymptotically expand it. Here's the asymptotic expansion of the Fresnel function, all right? I don't want to get deep into this, but we're going to keep only this leading term and this step function that's part of the asymptotic expansion of that. So this is the first term in the asymptotic expansion, all right? So here's Sommerfeld's exact solution. We take this Fresnel function with this argument and apply this asymptotic expansion and keep only the first two terms. One of them is a step function given by this, and the other one is the leading term of the asymptotic expansion. And re-express this using this asymptotic expansion, and we get the following for Sommerfeld's diffract. So this is the asymptotic expansion of Sommerfeld's result. All right. So U incident and U reflected are there with these step functions, right? That come from this. And then we have this whole thing, which we're going to say is U diffracted. But really, this is what's left after you do the asymptotic expansion. This applied to this and this. Look what happens real quick. You have sign in this argument. But here we're going to move that sign to the denominator because the argument is x in the asymptotic expansion. So then we end up with a 1 over sine. And then 1 over sine is cosecant. So that's where these cosecants come from. All right? Okay, so we got those cosecants. Very good. Now, if you compare this to our diffracted field, we're going to see that this is chi I and chi R. So let's do that. So here is our asymptotic expansion of Sommerfeld's half-plane solution. Let's compare it now to our expression for the diffracted field, which is here. And what we find then is the hard and soft diffraction coefficients, which this one is, I think this is D soft, this one's D hard, I think. Don't quote me on that. But yeah, the minus is the soft. We find our diffraction coefficients like that. by comparing an exact solution to our diffraction formulation. Okay, good. Now, if we let, the origin be at phi prime equals to alpha plus or minus pi and so forth, then we can rewrite that as this. So we're redefining the origin to line up with this cylindrical coordinate system. So we can use these variables instead of alpha. All right, good. So I want to get through this problem. So this is an example that I did for you guys. And this is a comparing Sommerfeld exact, the series solution we learned last semester, and we're going to do the geometrical theory of diffraction solution for this half-plane problem. So here we have the same half-plane. The incident angle of the plane wave here is 30 degrees. And we're going to observe the total electric field along this line at a distance of 2.25 lambda above the half plane and from 6 lambda to minus 6 lambda in x. And we're going to compare the total field for the Sommerfeld exact with the Fresnel functions, the series solution we learned last semester for scattering from a wedge by a plane wave, and the GTD, we're going to calculate the GTD solution. So for a half plane impinged upon by a plane wave, we're going to do both EZ and H pole problems separately. Plot the total field along the path shown using exact Sommerfeld, exact series from ECE 5105, and the Keller GTD solution, all right? The exact Sommerfeld solution for EZ is here. We already derived that, right? And we identified the Fresnel function, rho, and theta here in this particular geometry of this problem, all right? For the problem above, alpha is 30 degrees or pi over 6, so we can replace all these alphas here with pi over 6, right? And we get the following. For H-pole incidence, which is HZ, we get the same expression here, but we use a different coefficient here. So it's minus and plus instead of minus. Why is that? Because one of them's hard diffraction, one of them's soft diffraction. The polarization the soft or hard diffraction depends on the polarization, all right? This is like TE and TM that we studied last semester. The problem we studied last semester is here. The exact series solution of 5105 was this. So we had a line source, but we moved the line source out to infinity, and we used the addition theorem of Hankel functions in order to find the plane wave scattering solution from that wedge, right? And now we'll just take the wedge angle to 0. So that wedge angle alpha goes to 0, you get a half plane. And that's this solution here. I don't know if you guys remember this. So this is Bessel function, and we have sine of m over 2 phi prime, sine of m over 2 phi, and then we sum over this, which comes from the series solution. This is the mode matching thing, right? So since the angle theta, or phi prime, is defined from the top face, then see phi prime is measured from the top face. So that means phi prime is 7 pi over 6 for us because our incident plane wave, remember our incident plane wave is like this. So instead of alpha being 30 degrees, it's all the way to here, which is 7 pi over 6. You have to add pi over 2, yeah? In order to write our series solution from last semester in terms of that geometry. So we get this, right? And the exact series solution for HZ from last semester for a TE to Z plane wave incident from 5105 is this following expression, all right? Where we have cosines now. And then we have this operator here, which is like that. All right, since the angle phi is measured from the top face, we do the same thing again. And here we started from 0, now we start from 1. This series always starts from 1. So we have this 0th order term here, all right? And that's what this thing also is there. All right, that was from last semester. All right. Now, let's do GTD. So for Keller's GTD, for this solution, we first need the geometrical optics solution. Thus, we began by defining our shadow indicators. So our shadow indicators, here's the incident plane wave, right? So it's lit. This is the only dark region here, right? This is dark. So to find that, we say alpha going from 0 to alpha, the shadow indicator is 1 because the incident field is in the dark right there, right? And everything else is lit. Good. For the reflected field goes like this, like that, right? So it's dark over here, but it's lit in this region. So everything from here, this is the reflection shadow boundary. Everything in here is lit, right? And all of this is dark. Everywhere else is dark. So you get this expression, all right? Now that we have the shadow indicators, we can write the geo field as what we know and love. And that is z hat, because z hat polarized. The incident field here is this incident plane wave that we said is incident angle of 30 degrees. Like that, yeah? And then we have the reflected field and the shadow indicators. For the HZ polarized plane wave, it's very similar, except now we have this, right? The electric field has a reflection coefficient, makes it minus for a reflective field when you're tangential to the PEC. But the other component, which is HZ, is normal to it, doesn't have a -1 reflection coefficient, right? So that's why this sign changes. All right. So now that we have the geo solution, let's compute the diffracted field to complete the GTD solution. The diffracted field is given by this, which we already derived. Now we know what these are by comparing this with the Sommerfeld exact series or exact solution from a scattering from a plane, half plane. Okay, so here's our diffracted field. Now let's calculate what these diffraction coefficients are. Let's calculate the divergence factor. Since we have plane wave incidence, then we know R naught I is equal to infinity. It's a plane wave, so it has an infinite radius of curvature. Also, since our diffracting edge is straight, kappa is equal to 0. It's an infinite half plane. Thus, this was our expression for the diffracted field's radii of curvature, right? So 1 over R0 incident is 1 over infinity, that goes to 0. Kappa is equal to 0, right? So that means this whole term goes 0, we get 0. So 1 over R1 is 0, right? Okay, good. Which gives a divergence factor equal to 1. So that means this is equal to 1. All right. Now, since our incident field is Z polarized always, it's either HZ or EZ, our incident rays are approaching in the XY plane, right? So theta incident is 90 degrees always. That puts you in the XY plane, right? All right, so now we find the diffraction coefficients. Since in the XY plane, the theta hat unit vector always points in the minus Z direction. So let me write this. Z, X, Y. We're talking about everything happening in this XY plane, right? So that means theta is always 90 degrees. All right, and the theta hat unit vector here is always minus Z hat. All right. Also, the phi hat unit vector we can express in terms of negative sign, in terms of Cartesian components, right? Cartesian vectors. All right, but now we're saying this is theta because in our problem here, this polar angle was called theta. All right, so we just need to make sure the azimuthal variable we're going to call theta. Where are we at here? Yeah. All right. Okay. Good. So now since our incident field is given like this, and we want E incident at the point of diffraction, then rho goes to 0, right? That's how you get, the rho starts at the point of diffraction, thus giving E theta incident equal to 0. Yeah. So it's E phi only, right? E phi only. That's right. Okay, now the diffraction coefficients we can calculate. We know what alpha is. It's pi over 6, right? Alpha is our angle of the incident plane wave, right? So we know what that is. That is here. We know what that is. We can plug in pi over 6, right? Okay. And the soft and hard only differ by this minus and plus, all right? Theta is the observation, azimuthal observation angle now, right? Okay. So let's put it all together now. And we find the diffracted field to be e to the I k rho plus pi over 4 over, this comes from our g of k rho, right? And here's our diffraction coefficients for this particular geometry for the, so this is the diffracted field, right? Now, the EGO solution, the total solution now, GTD solution, so this should say GTD probably, is incident plus reflected plus diffracted for this polarization, all right? And the HZ for the other polarization is incident plus reflected plus the diffracted. Notice this is different. This is different because the reflected field for this polarization does not have a -1. It's normal to the plane. All right? So I wanted to get through all that so you could see this. Here we have the solutions now. So here's our problem here. We're going to plot the field from -6 lambda to 6 lambda, -6 lambda to 6 lambda, -6 lambda to 6 lambda, all right? What am I plotting? The two solutions. Here's the EZ polarization solution. Here's the HZ polarization solution. EZ is soft pull, HZ is hard pull, the way we've set this up. And what were we comparing here? So, all right, so let's look at this one first. So we have a plane wave coming in against this, and we're going to generate, we're going to calculate the solution. Sommerfeld exact is the blue curve. All right? Sommerfeld exact, that's an exact solution, analytic solution for the scattering from this half plane by a plane wave. The exact series we solved last semester, that's our modal expansion in terms of cylindrical wave functions, right? So Sommerfeld exact and exact series solution are overlapping. That's why you can't see the blue one. They're both exact. They better overlap, right? Okay, now we have geometrical optics. So what's happening here? Here's geometrical optics. This is the total field. So at some point, the incident shadow boundary here is here, right? At that point, we have 3.8971 lambda. So this point here is 3.89 lambda, right? So after this, we have, this is lit, this is shadow, right? So there's a sharp discontinuity in the total field for the rest of this part of the plotting range, right? It's in the shadow boundary. Now the GTD solution looks very good. So you get all this ringing effect, right? That you don't get. The edge causes ripples, right? Like Fresnel and all that. You get these ripples from the diffraction, right? The GTD solution predicts that very well. And it starts to converge to the exact solution away from the shadow boundaries. That's the problem with GTD. GTD predicts infinite field at the shadow boundaries. Why is that? Because these diffraction coefficients, they blow up at the shadow boundaries. All right. So they blow up at the shadow boundaries. So GTD looks good away from the shadow boundaries. All right. We're going to solve this problem, and we're going to come up with a ray diffraction theory that follows the exact curve. Instead of using GTD, we're going to use UAT, which is part of your reading in your homework, and UTD. We're going to study both those next lecture, and they recover the correct behavior in here. All right? It fixes the problem with GTD, which is infinite field along the shadow boundaries. All right? But away from the shadow boundaries, the GTD solution is very, very good. It predicts all of this ringing and all of that, right? So we're going to come up with these things called detour parameters. We're going to use a ratio of Fresnel functions for one approach, and we're going to subtract this singularity here from the incident and reflected fields in another approach using the Fresnel functions as well. All right, that's UTD and UAT. So, okay, so here's HZ pole, which is the hard pole problem. Here we have incident magnetic field, so we're looking at the magnetic field instead of the electric field, and we see that there's less ripple for hard polarization, but still we have the same problem with the GTD solution becoming, so it's very, very good away from the shadow boundaries, right? We're going to keep that part of the solution of GTD when we do UAT and UTD. But we're just going to augment this central part with something else, right? You guys will read about that in your homework as well. And we're going to study it next lecture. All right. So so this clearly shows what the problem is with GTD. The diffraction coefficients blow up at the shadow boundaries, but they work very well here. Geo does not predict any of this, right? It's a plane wave, so it has uniform amplitude everywhere. So if I look at the plane wave all along this points until I get to here, then I get the same value, right? It's a plane wave, but that's really not what's happening. Really, what's happening is the field is ringing here because this diffracted field from this edge, the diffracted field from this edge is interfering with the incident field there. And it's causing this interference fringes. Yeah? Okay. So we did GTD in one lecture. We're done. GTD is done, all right? So next time we're going to look at UAT and UTD. And then, we're going to add one more thing to GTD, rather. We're not completely done. We have to look at wedge diffraction coefficients. We only have the diffraction coefficients for the infinitely thin plane, half plane. Now we're going to look at, for sharp edges. Now we're going to extend it to wedge. next lecture. And then we're going to do UAT, the asymptotic theories, and the uniform theories. Uniform theory of diffraction, uniform asymptotic theory. Then we'll be done with array-based techniques. We'll be done. The last lecture, which is next Wednesday, a week from today, is going to be Green's functions. We'll look at, how to construct Green's functions and things, and that'll be the end of our course. All right? Okay, you guys learned a lot in this semester and last. If you combine both these semesters, we did the entire book and we added a bunch extra stuff that I threw in there for you. But same topics, but expanded. So now you're all advanced electromagnetic engineers. All right? Good.